All right, let's come back after the break. So let's continue with the Taylor series. So what actually is a Taylor series? Now we have a smooth function. A smooth function means the function with derivative of all order exists. And we try to represent whether that is approximation or not depends on how many terms you use, okay? We try to represent that function using a power series. So instead of writing that function out explicitly using the formula that you are given, we want to represent it, we want to be approximated with a polynomial, okay? The polynomial is this form. When my x, when the x that is an independent variable is sufficiently close to a fixed point, which I call x naught, then the function can be represented by the following series. The series consists of the constant term, which I call a naught. Okay, that is a constant term, and a linear term that is proportional to x minus x naught with a constant a1, quadratic term x minus x naught square with another constant a2, the cubic term x minus x naught to the power 3 with a constant a3, and so on and so forth. And in principle, the series is an infinite series. It goes to infinity. That it consists of infinitely number of terms. Okay. So if you are a mathematician, you may be interested in asking the following question. You say x is close to x naught for this expansion to valid. So how close should that be? And is the representation is possible in general for any function? You mean you can represent it with a polynomial? If this is possible for all functions, then how to prove it? Okay. This series actually consists of an infinite number of terms, right? So does the series converge to the function? If I add infinite number of terms, will the series go up and down without converging? Then that would be a problem. We actually leave all this question to the mathematicians. We are not going to teach it to how to prove all this in this course. But for physicists, we are interested to know how to do it. And we are interested to know under what condition will this be a good approximation. Okay. So what we are going to do is that we have a function f as a function of x. And when we are getting close to a certain fixed point that I call x naught, then I'm interested in finding a polynomial like this, which is a close approximation to the original function around this point. Okay, so that is the task we want to do. Okay, and I told you the answer beforehand. Okay, so I want to find such a polynomial. So that means I want to determine the coefficient a0, a1, a2, a3 up to a infinity. Okay, this is my only task. I want to find a suitable series of constant a1, a0, a1, a2, a3, a4 up to an. Okay, so that my polynomial will be getting will represent the original function at a point x0 close to that point x0. Okay. And it turns out that the coefficient a1, a2, a3, they are given by the following. Now, whenever I highlight the part of the function in red, that means that they are the coefficient. The coefficient are constant. They are numbers, okay? They are the numbers, but not a function. The functional dependence is on the back part, x minus x naught term, x minus x naught square term, x minus x naught cube term. They are the functional dependence. And all this coefficient a0, a1, a2, a3, they are a certain constant. So how to find the constant a0? A0 is the original function, but evaluate at the point x0. that we make the expansion. How about A1? A1 is the first derivative f prime of the original function, but evaluate at the point x0 divided by 1, but which essentially is f prime x0. How about A2? A2 is the second derivative of the original function, evaluate at x0 divided by 1 times 2. And for the third, for the A3, it's its third derivative evaluate x0 divided by 1 times 2 times 3. So these are the results. Okay. I will explain it to you later. I'm not going to prove it, but I'm going to explain it to you later why making such a choice will help you represent the original function. Okay. Now, in general, what is about the coefficient of the n term? The coefficient of the n term is the nth derivative of the original function evaluated at x0 divided by n factorial, where n factorial is 1 times 2 times 3 times up to n. Okay, if you have 1 factorial, that is 1. If you have 2 factorial, is 1 times 2, that is 2. If you have 3 factorials, it's 1 times 2 times 3, and so on and so forth. That is n factorial. Okay, so the coefficient for the term with the power n, x minus x0 to the power n, is given by the n derivative evaluate x0 divided by n factorial. So that result in an infinite series with the coefficient of the n term given by this. Okay, and that is called a Taylor series. Now, so I'm not going to prove why this coefficient are so and so forth, but I'm going to let you know the physical meaning of that. Now, let us take the derivative of this series. Now, I denote the series representation of the function by fs, and the original function is f. F is the original function, and the series representation is given by fs. Is denoted by fs. So I take the derivative of fs. Okay. How about the first derivative? The first term is a constant, so I get rid of it. The second term is x minus x0, so I differentiate it. I only differentiate the x, and that gives me 1. And so that gives me a constant factor of f prime x0. Is that right? How about second term? The second term is x minus x2 squared. So when I take the derivative, it becomes 2x minus x0. Is that right? And the 2 will cancel with this 2 in the numerator, in the denominator. So I got f double prime x0, x minus x0. And similarly for the third order term. So the third order term becomes second order after a differentiation. And the constant 3 cancel with this constant 3. And so in the prefix, I get f triple prime and x0 divided by 2. And for the fourth order term, I don't write all the term out, but for the fourth order term, the differentiation of that will give you a dependence of x minus x0 to the power 3. The symbol O here, you see I write a curly O. It just means that the remainder terms is at least of the order of x minus x0 to the power 3. It may be of high order. It may be to the power 4, to the power 5, to the power 6. But the lowest order of the remaining term is of the order of x minus x0 to the power 3. Okay. Now you can repeat this process. You can do the derivative again to find the second derivative of the series representation. So this term vanish because it's constant. This term is linear, so I differentiate it. It just gives me a constant f double prime x0. This term I differentiate it become x minus x0, right? And 2 goes in front to cancel with this 2. So I get f triple prime x0, x minus x2, x0. The order 3 term, when I differentiate it, become order 2, right? And I can proceed one step further to get the third derivative. Okay, do you get my point? So now I have the first derivative, second derivative, and the third derivative of the series representation. Okay. Now I find an interesting fact is that when I put x equal to x0 in this series, Okay, when I put x equal to x naught in this series, all the term that depends on x minus x naught to the power n, they will vanish because they are 0. When I put x equal to x naught, x minus x naught to the power whatever is 0. So for when I put x equal to x naught in the first derivative of the series, I only get f prime x naught, right? I only get f prime x naught. So that means the series, the derivative of the series as x naught is equal to the derivative of the original function at the same point. And again, if I examine the first derivative of the second derivative of the series, and when I put x equal to x naught, again, I get rid of these two terms, and all the subsequent terms, they are 0 because it contains terms that goes at x to the x naught, x minus x naught to the power n. So they're all 0. And I only get this constant. So that means the second derivative of the series solution when I evaluate x naught is equal to the second derivative of the original function at the same point. And if I examine the third order derivative, they are the same too. Okay. And in fact, if I do it for infinitely many terms, I find that the derivative of the series and the original function for all orders, they match at the point x equal to x naught. So that means at that point, at that particular point x naught, the series has a derivative at all orders equal to the derivative of the original function. Okay, so that is the idea. Okay, so let's see how it will help us to make an approximation. Now, let the original function be f, and f will represent by the blue line. So that is the original function. And now I examine upon a fixed point I call x naught. So if I write out the series that consists of infinite many terms, but let's pick out the first term. The first term is a naught. Okay, but a naught is just a constant, and a naught is just the original function, but the value of the function at the original point x naught, right? So again, so this function, this constant function, is just give me a horizontal line. Okay, and this function fs and the original function f, they only agree at one point. That point is x naught. So that is not a good approximation, right? And how about if I add a linear term? Instead of just a naught, I add the term a1 multiplied by x minus x naught. So what will happen with that? Now, according to our previous discussion, the coefficient a1, now this is of course a straight line, right? You can see this is a straight line. But the coefficient a1 is fixed such that the derivative of this function, this series, this polynomial has a slope that matches the original function. Okay, because the first derivative match, that means the slope of the tangent will match, right? So that means the straight line has the same slope as the tangent of the original function. Okay, so that means the straight line is actually the tangent to the original function, right? Now, so you can see it become better now. The straight line here will become a better representation to the original function. So you can see that the difference between the dot line, the dashed line, and the blue line, they are getting close when I'm close to x naught. Okay, so that is a linear approximation. I'm making a linear approximation of the original function. I make the function value at that point match, and also the slope of the function at that point also match. How about if I add the second order term? Instead of just having a and a1, I add a2 multiplied by x minus x naught squared. And in our previous discussion, we find that the second derivative will also be getting matched, right? So I'm using what? I'm using a quadratic formula, a quadratic graph. This is a parabola, right? A function with a dependence of x and x squared is a parabola. Now I'm using a parabola to approximate the original function. And the parabola is such that the value of that function of the parabola at this point, the first derivative and the second derivative matches with those of the original function. Okay, so I match the derivative up to the second derivative. And if I add one more term, I add the x minus x naught cube in this series, then I'm still making an even better approximation. Okay, I now match the derivative up to the third order. Okay, so by adding more and more terms to the series, I am actually matching the derivative of the power series with that of the original function to the higher order. And that means the two functions will become getting closer and closer together. Okay, so you can see from this to this to this to this, my approximate function, which is denoted by the dashed line, is getting closer and closer and closer to the original function, which is denoted by the blue line. Okay, but that representation holds only when I'm getting close to this point x naught. Okay. So let me have an example for you. I have an exponential function e to the power x, and I want to find the Taylor series of this exponential function about the point x naught equal to 0 up to the order of x cubed. So I neglect terms that goes at x4, x5, x7. I only represent the function using a series up to the third power of x. Okay. Now the Taylor series tells me like this. The series will be given by this. Now I just let you see the series again. And if I put x naught equal to 0, okay, I expand it about the point x naught equal to 0, which is a fixed point. This becomes 0, this becomes 0, this becomes 0, this becomes 0. I evaluate the derivative at the 0 point, right? And also the polynomial in the polynomial here, I got x naught 0, x naught 0. So they will become x, this become x squared, this become x cubed. So I get this series. Okay, now this series is sometimes called Maclaurin series. When x naught is equal to 0, the Taylor series is sometimes called the Maclaurin series. Okay. Now, so I have to find the derivative of the original function. So I have to find the derivative of ex to the third order. But that is an exponential function. So no matter how many times you differentiate it, it just returns to exponential function. It won't change. And if I evaluate all this derivative, the function itself, the first derivative, second derivative, third derivative at the point x equal to 0, what I get is just 1. Because e to the power 0 is just 1, right? So I put back all this constant into the coefficient, right? So this is 1, okay? This is 1 divided by 1, or the coefficient is 1. This is 1 divided by 2, this is 1/2 x squared. This is 1 divided by 2 times 3, this is 1/6 x cubed, and so on and so forth. Now I expanded only to x cubed. I neglect the higher order. So this is my series representation of the exponential function when I'm getting close to the point x naught equal to 0. So it may be very abstract to look at this polynomials. So let us look at this graphically and see what happens. Okay. Now this is the black line here is the exponential function. Okay. This is the exponential function e to the power x. That is the original function. We want to find the approximation when I'm getting close to the point x equal to 0. X equal to 0 is here. At x equal to 0, the function has a value of 1. Okay, because e to the power 0 is 1. So the first term in the series representation is 1, right? So this is a simplest constant term, which is actually not an approximation at all. It's only representation of the value of that function at the point x equal to 0. So it's y equal to 1 is a horizontal line. And in the next approximation, we add the linear term. The linear term makes it to be a straight line with a certain slope. And when we make the slope to be equal to the slope of the exponential function at x equal to 0, we got this blue line. Okay. So the blue line is y equal to 1 plus x. Okay. How about adding another term which goes at 1 half x squared? So I get this green line. The green line is a quadratic function. Okay, it's a parabola. Okay, because it consists of a constant term, a linear term, and an x squared term. So it's a parabola. And the parabola is matching better to the original function now. Okay, so you can see the parabola, the green line and the black line, they are very close. But still we can make it better by adding the cube term. Okay, and that becomes what? That becomes the purple one. Okay, the purple is a cubic approximation. And you can see for y ranges, the exponential function are very close to this cubic function. Okay, the purple line and the black line, they are getting very close together about the point x equals 0. Okay, so imagine if you are adding infinitely many terms, the series solution will be getting closer and closer to the original function, and that eventually will result in the exact representation of the original function. Okay, now how to prove that? That is a mathematician's job. That is not my job. My job is only to introduce the series to you, let you know how to do it, and also I will let you know by taking the first few terms of the series, you will be able to find an approximate representation of a function using a power series. Okay, using a polynomial essentially. Okay. Again, another example. I have a sine function. I want to make the power Taylor series expansion about the fixed point theta equal to 0 up to the term order of theta to the power 3. Okay, so I write out the Taylor series up to the term theta cube. Okay, now the sine function is when I take the first derivative, it becomes cosine. When I take the second derivative, it becomes minus sine, right? When I take the third derivative, it becomes minus cosine. Okay, when I evaluate the sine function as 0, it becomes 0. When I evaluate the cosine function as 0, it becomes 1. And when I evaluate the minus sine function as 0, it becomes 0. And when I evaluate the minus cosine function as 0, it becomes minus 1. So I now got all the coefficients. So I put it back to here, to here, to here, and here. I got this series. And you can see in this series, the even power vanish. This vanish, this term vanish. So eventually I got the sine theta can be represented by theta minus theta cube over 6 up to the third order in theta. Okay. Now in your homework, you will be asked to do the same thing, but now for the cosine function. Again, I want a accuracy up to the third power of theta. And you will find that a cosine function about theta not equal to 0 can be expanded in as a series of 1 minus theta squared over 2. It can be approximated by this function. Okay, so that is your homework. You just repeat what I've done in lecture, but just replace the sine with the cosine, and you will get this result. Now let's see the interesting to see the graph. I like seeing the graph actually. The original function is a sine function, right? The sine function goes like this. Okay, but if you represent it with only the first term, which is a linear function, which is theta, just theta, you are just drawing a straight line with a slope equal to 1, right? And this straight line just have the same tangent as the original sine function at a point x equal to 0. They have the same slope, okay, at x equal to 0. If you add a theta cube term, okay, you will end up as a blue line. Okay, the blue line is still even a better approximation. If you are not satisfied with that, you can add the term with the power with theta up to the power 5. Now the coefficient for the theta fourth power is 0. So the next term goes to the theta to the power 5. If you add the terms up to theta to the power 5, you will get the green line. You can see the green line is a better approximation to the sine function than the blue curve. And so you can get you can also add the higher and higher order. You can add as many order as you like. Okay, and that will become the exact sine function if you add infinite many terms. Now let us connect what we have learned now about Taylor series with what we learned in high school. In high school, you learn about the sine function and the cosine function when the angle theta is small. You learn how to approximate them, right? And that approximation is actually used when we take limit of the function sine and cosine. Now this is a point xy on the coordinate plane, and the y coordinate is the height, the x coordinate is the horizontal distance from the origin, and when I express it in a polar coordinate, this distance is r. We consider a fixed r. The radius of the circle is fixed, and this angle is theta, right? Now, what I call sine theta is actually y over r. Okay, the opposite side divided by the hypotenuse. But I can see when my angle theta is getting very small, then the vertical height y here is almost equal to the arc length subtained by this angle theta. The arc length subtained by the angle theta is s. Okay, so when theta is small, y and s, they are almost equal. Okay, so I can replace my y with s if my theta is sufficiently small. And in that case, I realize that s over r is just the angle theta expressed in radian. That is the definition of the angle in radian. The radian is the arc length divided by the radius. Okay, the arc length subtained by an angle divided by the radius of that circle. So I now have an approximation of sine. When the theta is small, sine theta is equal to theta. Remember that in doing this approximation, my theta has to be given in radian, not in degree. Okay, and how about cosine? Cosine is x over r, and when my angle is small enough, you can see x and r, they are almost equal, and so x over r is almost 1. Now, what we call the Taylor series is actually a correction to this. Now, remember what we got for sine theta up to theta cube term. It consists of the first term is theta, and the second term is theta cube divided by 3 factorial. You can see the first term exactly match our limiting case for theta. Okay, and the theta 3 term and the theta 5 term, etc., they are the correction to that. Okay, and for the cosine, at theta 0 exactly 1. And for a small correction to that, you should add theta squared over 2 factorial with a minus sign. And you can have a better approximation by adding more terms. Okay. Now, I let you I try to let you do it in class. This is a power series of 1 plus x to the power alpha. Okay. How to do it? How to expand it? If I expand this function about the point x not equal to 0, what I get is this series. Okay. And so please write down the derivative of this function and the second up to the second derivative and evaluated the function and its derivative to at the point x equal to 0, and you got the coefficient, and you put the coefficient back. You got the Taylor series. Now try to do it now. I just give you 5 minutes to do it. Okay, so pick out a piece of paper, try to work on it. So have you got the answer? I worked out together with you. Okay. So we have the function like this. And we want to find the Taylor series of the function. At around about the point x equal to x naught. Okay. So the first term is the value of the function at x naught. The first term consists of the first derivative over 1 factorial. That is with the x. And the second order term is f double prime evaluated as 0 divided by 2 factorial x squared, and so on and so forth. Now my original function is 1 plus x to the power alpha, right? So I take the first derivative, it become what? It become alpha 1 plus x alpha minus 1, is that right? When I take the second derivative, it become alpha multiplied by alpha minus 1, 1 plus alpha minus 2. So how about if I evaluated this function, this and its derivative at the point 0? Of course, when I evaluated the 0, it become 1. The original function become 1. And the first derivative, when I evaluate it to be 0, this become 1. And this become just alpha. And for the second derivative, when I evaluated this as 0, this is 1. And the second derivative become alpha minus alpha multiplied by alpha minus 1. Okay. So I put all the things back to the series again. And so the first term is just 1. The second term consists of alpha divided by 1, which is essentially alpha. And the second order term is alpha multiplied by alpha minus 1 divided by 1 multiplied by 2x squared. So this is the power series. Okay. Now, so I share the screen with you. I stop the sharing first. So I put the whiteboard content in the chat box, so everybody can download it. Okay. So what we got is this result. So what we get is this result. Now you may go ahead to look at the coefficient for a general term. The coefficient for a general term is x to the power n, the coefficient of that. You should be able to find that, okay? And not difficult. You differentiate n times, and then you evaluate the function at as x equal to 0, okay? Now if alpha is, now there's an important thing to note. If alpha is an integer, for example, if alpha is an integer like 4, 5, and 6, then you will find that actually this series expansion will give the expansion of this function in terms of a binomial formula. That is the usual binomial formula you got in you learned in high school, and you only got a finite number of terms. For example, if alpha is 7, then you get 8 terms. If alpha is 8, then you get 9 terms. So you get a finite number of terms if alpha is a positive constant. Okay. Now, but if and that expression is exact. Okay, you don't have a higher order. But if alpha is a fraction, or if alpha is a negative number, then this expansion consists of infinite number of terms. Okay. And that will be an approximation, but not the exact representation of the original function. It depends on how many times you take. Okay, it is an infinite series that represents the original function. Okay, so that's an important difference between alpha as being a positive integer and alpha being a fraction or a negative number. Now, I want to talk about a little bit about approximation skills. Now we have the Taylor series of some common function given by this. This is the function, the binomial expansion that we have just encountered. This is exponential function. We also work on it. The sine function and cosine function, and also the logarithmic function can also be expressed in terms of the series. When c equal to 0, the log 1 is 0. So that is a power expansion about the 0 point of this function. Okay. So you don't need to remember all this series. Just try to remember 1 or 2 terms if you can. Okay, that is useful because we frequently use it in our course. Now, why are we interested in making approximation? If we have an exact expression on a physical phenomenon, why bother to make an approximation to that? Okay, you may ask this question. But the reason is that an approximation can help us simplify the formula. And so you will get a better sense of how various physical quantities are related. If you are given a complicated function, sine or cosine, and a lot of complicated dependent, when one of the variable change, you do not know what will happen to that function. Okay, it's very difficult for you to see how the function depends on that variable. But if you approximate that function, you make an approximation, and you simplify the function, you will get a better sense of how they are the quantities are related. And so that enables you to understand the limiting case, especially the limiting case. When, for example, some quantity is very large or very small, you know what will happen. Okay, so those are the limiting case. When certain quantity are very small, take on a very large value, on a very small value, you know what will happen to that physical system. You know how to predict the physical phenomena. Okay, and sometimes you are required to solve a complicated equation, and if you don't make approximation to that, the equation will be analytically unsolvable. You cannot simply express the solution in terms of simple function. But if you allow a certain approximation, you allow a certain inaccuracy, then you will be simplifying the expression, and you'll be able to solve, and you'll be able to solve that equation nicely, and end up with a solution in a closed form, which is beautiful, and you can look at the dependence very clearly. Okay, so that's why we want to make approximation. Now I take an example for you. We have seen this factor before. This is the relativistic factor, and it goes as 1 over square root 1 minus v squared over c squared, where v is the speed of the object and c is the speed of light in the vacuum. Now I haven't learned a special relativity before. Imagine you haven't learned relativity before, but just by looking at this factor, you can see what it means. Okay, in the limiting case. Okay, suppose the speed of an object v is much smaller than speed of light. Okay, imagine that when v is much more than c, then what will happen? When I have an object moving with a speed that is much slower than the speed of light, then v over c is negligible. V squared over c squared is negligible, right? So essentially, this factor becomes 0. And the square root become 1. And the factor gamma become 1. So that means relativistic effect is not important when gamma is equal to 1 or almost equal to 1. That means that we are having a low speed regime. And in that regime, the relativistic effect is not important at all. We can return to Newtonian mechanics. But how about if I have an object with speed getting close to the speed of light, then what will happen? If v is getting close to c, then this number, v over c, will be very close to 1, right? V over c will be almost 1. Is that right? Then what happens? What will happen to 1 minus v over c, v squared over c squared? It will be very small, right? When v squared over c squared is almost 1, 1 minus v squared over c squared is almost 0. And you have take the square root, and then you take the reciprocal of it. A reciprocal of a very small number will be a very big number, right? So you have gamma to be very large. And gamma very large means that relativistic effect is very important now. It allows you to see that when gamma is getting very large, relativistic effect, it means relativistic effect is very important and you cannot neglect it. Okay, so that is the idea. Even if you don't know how to derive this equation, just by looking at it at a certain limiting case, you know what those limiting case means and what physical result will be in those limiting case. Okay. Now let's apply this factor to the total energy of a moving body. Einstein showed that the total energy of a moving body is equal to mc squared divided by square root 1 of minus v squared over c squared. And I can write that gamma mc squared. Gamma is my shorthand, okay? Now this formula, you don't know how to derive it yet. But take a look at the limit. When my object is not moving, or when my object is moving, is at rest, okay? Then v is 0, the factor gamma is just 1, and E become mc squared. So that what the equation means is that the energy, the total energy of the body is associated with the mass of the body. The energy is equal to the mass of the body multiplied by the square of the speed of light. That is Einstein's famous equation. Mass and energy are actually equivalent to each other. Okay, mass can be converted to energy and vice versa. But how about if my v is not 0? I imagine that my speed is not 0, but it's much more than c. Then what will happen? I can do an approximation. I can find an approximation to this square root by using the Taylor series. Okay, so what I'm going to do is I want to expand this 1 over v squared over c squared raised to the power minus 1/2 because the square root is in the denominator. So I have the power equal to minus 1/2 when v squared over c squared is much more than 1, when v is much more than c. But now I have the Taylor series. I just found it, right? It says that when I have 1 plus a small quantity I call c raised to the power alpha, then the series goes like this. When c is much more than 1. The first time is 1 plus alpha c, the second time is alpha minus 1 over 2 c squared, and so on and so forth. I can only keep the first two terms. I can even neglect the second order. And in my mind, because of this expansion, I now identify c as minus v squared over c squared. It must include the minus sign because my expression is 1 plus c. So comparing with this, the c is minus v squared over c squared. And the alpha is minus 1/2. So I just follow the formula and I take the first two terms. The first term is 1. The second term is alpha, which is minus 1/2, multiplied by c, which is minus v squared over c squared. And I neglect even the second term, that the c squared term at the higher order. I neglect that. And so what would it be? This be? The first term is of course mc squared. The second term, after canceling the c squared and the minus sign, I got half mv squared. So at low speed, the total energy can be written as a sum of mc squared plus half mv squared. Mc squared, as I say, is the energy associated with the rest mass. It's energy associated with the mass of the body. But how about the second term? You immediately realize the second term is the Newtonian kinetic energy. So this expression actually includes the rest mass energy of the body and the kinetic energy. But when the speed limit, but in a limit where the speed is low, where the speed is much more than the speed of light, the two energies separate into two terms. One term is the rest mass energy, and the second term is the Newtonian kinetic energy. So that means at low speed, in the low speed limit, the relativity result reduced to the Newtonian result for the kinetic energy. So that is what the equation means. Now, you haven't done relativity before, but if you are able to handle this expression correctly and making an approximation correctly, you can see some of its important features, some of its connection with Newtonian mechanics. Okay, that is how physics work. Okay. Now, when c is small, I throw away the higher order term. Why I can do that? Because when c is small, you imagine that well, say Cauchy is 0.001, then Cauchy square is 0.0001, and Cauchy cube is 0.00001. So I can neglect the high orders. Okay, I can have a sufficiently high accuracy. And also, in the denominator of the coefficient, I have the n factorial. N factorial increase very rapidly with n. And so 1 over n factorial will go to 0 very, very rapidly when I go to large n. And so that's why these two reasons combine so that I can ignore the high order terms without introducing much error. Okay. So here are the steps of taking approximation. First, I have a complicated expression. Then I identify a small quantity in that expansion or large quantity, depends on what you are doing. I identify a small quantity. In this case, my small quantity is v squared over c squared. This is a small quantity. You may include the minus sign also. The absolute value of that is much more than 0. And you should always take a small quantity as a dimensional quantity, which is much more than 1. Okay, so 1 is for the comparison, and you should make the small quantity you call to be dimensionless and should be much more than 1. Okay, and you decide the number of terms that is the order you want to keep, and you make a Taylor series up to that order. And these are the steps for doing a suitable approximation. And you will be seeing it in a lot in this course and also in a senior level course. This is a very important skill in physics. Now, if you want to learn more about differentiation, and you learn about differentiation of some common fraction and the rules, and also about Taylor series, you can look at this module, e-learning module. Okay. Now I'm a little bit slow in this lecture, so I managed only to cover the mathematical supplement. But at the beginning, it's no harm to teach slower. And if you have any questions, you can ask me now. And in the next lecture, we will go to higher dimension, and we will talk about how to describe the motion of those higher dimensional motion by using the language of vectors. And we will have a mathematical supplement on the use of vectors and about the cross product and the dot product. How about the velocity is very, somebody asked me, how about the velocity is very close to the light speed? The energy becomes 0. No, it becomes infinite. The factor gamma, the gamma is 1 over square root 1 minus v squared over c squared. If v is getting close to c, then 1 minus v squared over c squared is very small. And 1 over square root of that is becoming very large. So that when the speed is getting close to the speed of light, the total energy of the body will be tending to infinity. So that places a limit to the speed of an object with a finite mass. It actually says that the speed of a body with a finite mass cannot exceed the speed of light, and the speed of light is a highest speed in the universe. Okay, because when you are getting close to that speed, the speed of light, the energy of the body is getting to be infinity. So that means you have to input a lot of energy to make the speed of the body getting close to the speed of light. And that places a limit to the speed of a body. Do I answer your question? Any more questions? Another question is, but isn't there some finding in years before mentioning maybe other stuff speed faster than light is discovered? Not yet. Not yet. We have not confirmed any experiment that shows the speed of an object with a finite mass can be faster than the speed of light. All the previous exception, so-called exception. They are a false alarm. And it turns out that they have done the experiment something wrong. And there is no experimental evidence which say that the body can have a speed that exceeds the speed of light. I think some of you are asking me about how to answer a question, how much is required to answer a question. But I do think that a reasonable answer. I think you can judge from the question how much you need to answer. You have to have a sense of that. I'm not expecting you to find, for example, the dimensional analysis problem. I'm not expecting you to write a lot of things about the constant c. I want you to use dimensional analysis to find out the dependence of that equation. And if there's a dimensionless constant, you just explain to me whether that constant can be determined by dimensional analysis or not. Okay, I'm not telling you to do an essay to explain the whole thing. So try to have a sense of, you are a university student now. So don't ask me how much I should answer. You should have a sense to judge yourself. And it's not very important to how much you should answer, but it's more important than how much you understand. That is more important. How much you actually learn. I think. Any questions? I better stop the recording.